Hey everybody, today we're going to talk about chemical reactions. So chemical reactions are probably what you thought of when you knew you were going to be taking chemistry this year. Unlike the math and the different types of measurement and things like that and the naming that we've been doing so far, you probably thought you'd be seeing some explosions and that sort of thing as we see different stuff react. So what is a chemical reaction? This is the process by which we take one or more things and we change them into different compounds. And so if you were able to look at a given substance and somehow know its chemical formula, which you can't really do that, right? You can't look at table salt and just know that it's NaCl. It would be really easy to see that it's changed, but we can't do that, right? So how are we going to know that we've changed from one thing to another? Well, it turns out that there are actually some pretty easily observed changes that indicate that a chemical reaction has taken place. So here are four. Number one, we might see heat or light being given off. That is indicative of energy being released. We might see a gas. Now, it's hard to see a gas, so you might see some smoke, but also if you have a solution, you might see bubbles. Bubbles are evidence of a gas. We might also see a precipitate. So precipitate, if you think of precipitation, precipitation falls. A precipitate is a solid product, and it is a solid that is produced that falls to the bottom of whatever our reaction vessel is when two solutions are mixed together. And remember, solutions are always aqueous, AQ. And then finally, we might see a color change. Now, before we dive into these reactions, we need to talk about some special elements. These elements are called diatomic elements. And I want to go show you where those are on your periodic table. So, first off, there are 7 of these diatomic elements, and conveniently, on our periodic table, they form the number 7. Now, if you're really keen on observing, you're going to notice that I've only circled 6 elements. So it turns out the 7th one is all the way over here. It's hydrogen. But hydrogen is kind of this special element, right? It's always an exception for a lot of different things. So this is one of those times. For the diatomic elements, it's the 7 that we've highlighted plus hydrogen as well. So what makes those 7 special? Well, those 7, it turns out, always exist in pairs of 2. So here they are with their subscript 2 written. And if we had an element like that hydrogen, it turns out hydrogen is not very happy by itself. It has this extra valence electron hanging out there. So what does it do? Instead of remaining by itself, it grabs another hydrogen that has its valence electron, it forms a covalent bond, and it exists as H2. And it turns out H2 is much more stable than H by itself. And so in nature, or if you just went out and you found elements, outside, it would always exist as H2, not H, which means if we encounter any of those 7 elements in a chemical reaction, we always have to give them the number 2 as a subscript. They always pair up. And so there are some different ways you can remember this. You can find the 7 on the periodic table. You can also remember the mnemonic Hunkelbrief or Brinkelhoff. Both of those are fun ways to remember those 7 elements. You'll hear us talking about those from time to time throughout the course of the year. So we have these reactions. Now, how can we show what reaction is happening? Well, we can write something called a chemical equation. So a chemical equation describes a chemical reaction. And in order to have a correct chemical equation, it must satisfy the law of conservation of mass. And we're actually going to do that in our next set of notes when we talk about balancing. So for today, what our goal is going to be is simply to take words and turn them into this chemical equation. And you'll notice that we've given you this nice little table of different symbols that can be used in chemical equations. And so we'll get some practice doing that. Now, you'll need to remember your naming rules as we go along and do this. So we're going to write chemical equations for the words that are given. So first off, we're told that we have gaseous chlorine. Well, that actually means a great deal to us. So gaseous chlorine, we know that chlorine is Cl. We are also told that it is a gas, so we are going to put the letter G, meaning gas, as a subscript down there in parentheses. But also, if you remember Brinkelhoff, or your number 7, it turns out that chlorine is one of those things that always gets a 2 by it. So it needs to be Cl2, not just Cl. We're told that that chlorine reacts, so we are going to put reacts as a plus sign. This looks a lot like a math problem. Reacts with aqueous potassium bromide. So potassium bromide, remember your naming rules. Potassium is K plus 1. Bromine is Br minus 1. So if you cross those together, you get simply KBr. We are told it's aqueous, so we're going to put AQ in parentheses. And we are told that they react together to form. So to form is this arrow. Another way of pronouncing that arrow is to say yields. So you could say Cl2 plus KBr yields, or they form liquid bromine. So liquid bromine is again going to be Br. We're told it's state of matter, so we're going to put an L for liquid. And remember, bromine is part of Brinkelhoff. It's the beginning part, so it gets a 2 by it. You always have to be aware of those 7 elements to make sure they double up because they're diatomic. And we're also making one other thing. We are making an aqueous solution, we are told, of potassium chloride. So potassium chloride is KCl plus 1 and minus 1, and this, we are told, is aqueous. So our completed chemical reaction is, or a chemical equation that describes the reaction is Cl2 plus KBr yields Br2 plus KCl. And that's good for right now. Some of you who are really on your toes are going to notice that we have only 1 Br on the left and 2 on the right, and that seems problematic, and there's a similar issue going on with chlorine, and you're right to be concerned about that. We are going to fix that in the next video when we talk about balancing. For right now, let's see if we can continue turning these words into equations. So solid aluminum. Solid aluminum is just Al with an S by it to indicate it's a solid. Some of you might be wondering, why am I not putting a 2 by that? Well, remember, aluminum is not one of your 7 diatomic elements, so therefore it does not get a 2. We are told it reacts with solid iodine. Iodine is one of those 7, so iodine is going to be I2, and we're told that it is a solid. Let me fix my plus here. And it says that it is going to produce solid aluminum iodide. And for aluminum iodide, remember, it's tempting to do something like this, right? ALI, aluminum and iodine. But we know more than that. We know that aluminum is a +3 charge. We know that iodide is a -1 charge based on the location on the periodic table. And so that means that we have to show that here. And so the correct formula for aluminum iodide is not ALI. It's ALI3 because you need 3 iodines to cancel out that +3 from aluminum. And we were told that this is a solid. Finally, jumping down to number 3. Number 3 says we are reacting solid magnesium. So magnesium is Mg. It is a solid, so we'll put the S. It is not a diatomic, so we don't need a 2. Solid magnesium is reacting with aqueous hydrochloric acid. So hydrochloric acid, if you remember back to your naming, is hydro, so it's binary. It's H plus Cl, so it's HCl. This is aqueous. And it is going to form aqueous magnesium chloride and hydrogen gas. So to form aqueous magnesium chloride, which is Mg and Cl, and we're going to come back and fix that in a second. MgCl, that's aqueous, and hydrogen gas. Hydrogen gas. Hydrogen is a diatomic, so it's going to get an H2 and it's a gas. So there's a lot going on here, and there's some questions that need to be answered because this is actually not done yet. So don't just stop the video. There's some things that we need to fix. First off, there's a question about both the HCl and the MgCl2. We've got an issue with both of those. And the issue centers around the fact that they both involve chlorine, and chlorine is one of those 7 diatomic elements, right? It's one of those Brinkelhoff elements. So here's a question. Why is it that up here in number 1, there's a 2 next to chlorine, but down here in number 3, there's no 2 next to chlorine? Well, the answer to that is the 7 diatomic elements only double up if they are by themselves. So if you have chlorine, walking down the street, and it's by itself, it's really not happy in this arrangement. It actually has 7 valence electrons, so it's in a situation where it wants to fill this vacancy right here. right? Chlorine's not happy with that. So if all it has around it is other chlorines, it's going to grab another chlorine that's in the similar situation. They're going to share that extra valence electron, and they're both going to be happy if they are bound together in ClCl or Cl2. But in the orange case, we have a chlorine with its 7 valence electrons, right? And it has an extra spot for that last valence electron. And it is going to bond with a hydrogen that has an electron to fill that vacancy. So this is why we do not need to write this as HCl2. In fact, that would be incorrect. This does not get a 2 because the chlorine is already happy with its full octet because it's found a hydrogen to fill the octet for it. Said another way, when you're writing out HCl, H is a +1, Cl is a -1, so you only need one of each of those to make HCl. Now, that brings us over here to this purple one. So Mgcl is what I have written, but we should be aware that Mg, based on its location on the periodic table, is a +2, and Cl is a -1. So really, if you cross those charges or you think about it, you need 2 chlorines to go along with that Mg. But we want to be very clear that this 2 is not, it is not because this is a diatomic element in chlorine. That is not why we have a 2 there. The reason we have a 2 is because Mg is a +2 and Cl is a -1. That's the only reason why there is a 2 next to that chlorine.